In this session, we will see what you mean by all-day efficiency, what is the importance of all-day efficiency, and some numericals on all-day efficiency. Efficiency of the transformer, we know that it is depending upon the loading factor as well as the power factor of the load. The knowledge of this efficiency is useful provided the load and its power factor remains a constant. Then only it is the importance of that is the load on the transformer, it should be a rated load, means with its full extent capacity multiplied by appropriate the power factor. Then you can calculate the efficiency, that is the transformer is well utilized. The transformer is well utilized for its purpose. But in the case of the distribution transformer, that is the distribution transformer is nothing but it is a catering the needs of LT consumers such as residential, commercial and other things. The load is not remains a constant. At the different interval of time, the load is goes on varying. Then it is not possible to find out the efficiency, that is the correct efficiency of the correct efficiency in the sense that is output and input. It is not a constant throughout. Therefore, it is very difficult to judge the utility or extent of usage of the transformer for a 24 hours. For that purpose, we are devising a all-day efficiency. Instead of calculating the efficiency in terms of output in terms of watts, that is the power, it is calculated in terms of output in terms of kilowatt hour, and the input is also in terms of the kilowatt hour, because the load is varying on the distribution transformer. Therefore, the transformer, that is the distributions on which are used to supply LT consumers, are called distribution transformers, and the load on such transformer vary widely over the 24 hours. Sometimes the transformer may be practically under no load condition, for example in the midnight, or it may be overloaded during the peak evening hours. Therefore, the loading is not remains constant. In that case, we are going for the all-day efficiency, that is, it is a ratio of output by input in terms of kilowatt hour. All-day efficiency, alternatively called energy efficiency, that is why it is called as a energy efficiency, because we are taking the ratio of energy output to energy input, is calculated for such transformers to judge how efficient they are. To estimate the efficiency for whole day, that is for 24 hours, is broken up into several time intervals. That is based on an average load for different times. It may be time blocks. 24 hours is divided into different constant load blocks. For example, 2 hours, 3 hours, 4 hours, 5 hours, 6 hours. For example, the 24 hours is divided into the different time intervals based on the constancy of the load on the transformer. For that particular period, what is its output in kilowatt hours? What is the losses in that particular period? Iron loss and copper loss. Similarly, for second period, what is the extent of loading of the transformer based on that output of the transformer that particular time period? What is its output and the losses you have to calculate? Then you have to sum up all the outputs for the 24 hours, and also you have to sum up for all 24 hours the iron loss, copper loss, and the output of the transformer for 24 hours, so that you are getting the input kilowatt hour. Then the ratio of the output kilowatt hour to the input kilowatt hour, that gives the all-day efficiency. The idea is to calculate the total amount of energy output in terms of kilowatt and total amount of energy input in the kilowatt over the complete day, and then take the ratio of these two to get the all-day efficiency. Just I am explaining with the help of here a table. All-day efficiency, by definition, it is energy output in terms of kilowatt hours in the 24 hours. That is why it is called as all-day efficiency. Energy input in kilowatt hours in 24 hours. What is the output in 24 hours and what is the input in 24 hours, that is in terms of kilowatt hours. In normal efficiency, you have got a kilowatt output by kilowatt input. And this energy input in kilowatt hours 24 hours is expressed in terms of energy output plus the losses for 24 hours. Therefore, energy output in 24 hours plus energy loss in 24 hours. Energy loss in 24 hours for the transformer, once again it is divided into the copper loss and the core loss for 24 hours as well as copper loss for 24 hours. Then I made a table that is 24 hours divided into 4 time intervals. It may be divided into 3 time intervals, it may be 4 or a 5, and the time period may be varied. T1 is not equal to T2, T2 is not equal to T3, T3 is not equal to T4. Means the sum of T1 plus T2 plus T3 plus T4 put together 24 hours, because we are calculating the output energy for 24 hours as well as the input energy for 24 hours. Means the depending upon the loading factor and constancy of the transformer, the time is divided into different blocks. Here I am taking 4 time blocks T1, T2 and 3 and T4, and the loading in this particular time period, that is in the first time block I have got a loading of the transformer is X1, and T2 time block I have got a loading of the transformer X2. Similarly, at T3 is X3 and T4 is X4. These are the loading of the transformer. And this particular time periods, I have got a different power factors, that is cos phi 1, cos phi 2, cos phi 3 and cos phi 4. These are the corresponding the power factor of the load and that particular time interval. Then the based on the loading factor, the based on the power factor of the load, you have to find out the output and multiply the time, that gives the kilowatt hour output for that particular time block. Therefore, what I am making here is kilowatt hour output. Kilowatt means what? It is the loading of the transformer multiplied by kVA into 10 raised to 3. Of course, we have to convert into watts, but it is expressing in kilowatt. Therefore, I am not multiplied here 10 raised to 3. Therefore, kilowatt hour output is the loading factor multiplied by the rating of the transformer multiplied by the power factor in that particular time period, and it is load is remains constant for T1 time period out of 24 T1 period. Then the total output in kilowatt hours what I am getting. At the same time, I know the copper loss at full load, but the transformer is loaded X1. Therefore, for X1 load, the copper loss is X1 square times copper loss at full load. But this is lasting for how many hours? T1 hours. Therefore, the copper loss for this T1 period, what I am calculating is X1 square copper loss at full load into T1. Similarly, for T2 I am calculating. It is X2 is a loading factor, cos phi 2 is the power factor of the load in that particular time period. Then I am calculating once again kilowatt hour output for that particular period. At the same time, I am calculating the copper loss. Such all the 4 periods I am calculating the kilowatt hour output, and sum of these gives the total kilowatt hour output for 24 hours. Because at the different time intervals, I have got a different loading factor of the transformer, I have got a different power factor. These are the different because of some of the loads are connected, some of the loads are disconnected in all 24 hours. It is not remains constant. That is why I am taking X1, X2, X3, X4. Then if you are adding all these kilowatt hour output, then you are getting kilowatt hour output for 24 hours. And what is the copper loss for 24 hours? You are adding all these copper losses, so that I am getting copper loss for 24 hours. Then I am getting kilowatt hour output in kilowatt output by adding these things, and the copper loss in 24 hours I am getting here. Then how to find out core loss in 24 hours? That is, I made a statement when we are explaining the efficiency of the transformer. The core loss is the remains the same irrespective of its loading factor. Therefore, straight away you have to take for 24 hours iron loss or core loss is iron loss multiplied by 24 gives the kilowatt hour iron loss for 24 hours, because irrespective of time for T1 is also the iron loss is remains same, T2 is also remains same, T3 is also remains same, T4 is also remains same. Sum of these T1 to T4 is 24 hours. Straight away I am making 24 into Wi is the total core loss in the transformer. Then once we know this things, that is core loss for 24 hours, core loss for copper loss for 24 hours, output in for 24 hours. If I know, then I can calculate the all day efficiency. We'll see some of the numericals, then it will give the clear cut idea about how we are calculating the all day efficiency. I've got a numerical, find the all day efficiency of 500 kV transformer, distribution transformer, whose copper loss and iron loss at full load are is given Wi and WCFL. First is given copper loss, then iron loss. You have to carefully you have to read the problem. First is given copper loss and iron loss. It is 4.5 kilowatt and 3.5 kilowatt respectively during a day of 24 hours. It is loaded as under. How the loading pattern? The number of hours is for 6 hours. It is loaded 400 kilowatt. He is not given a power factor. Directly he is given the kilowatt output. The power factor is 0.8. Then for next 10 hours, it is the loading output is 300 kilowatt with a power factor of 0.75. Next 4 hours, then it is output is 100 kilowatt and the power factor is 0.8, and number of hours, that is a 4 hours, last 4 hours, it is under no load condition. As such, there is no load connected to transformer, therefore output is 0. However, input is there for 4 hours. Even output is 0. Output is 0. However, the power factor is not come into picture because we are not loaded the transformer. You can see here, adding all these three, 4 time periods, the total is the 24 hours. The 24 hours, this is the loading pattern, and they are operating at different power factors. For such a transformer, you have to find out the all day efficiency. What you have to calculate? For 24 hours, what is the kilowatt output? For 24 hours, what is the copper loss? What is the iron loss for the 24 hours? And how to proceed this? First, it should be noted that load of 400 kilowatt, 400 kilowatt. I want at what load it is operating, so that I have to calculate the copper loss for this particular load. Therefore, 400 kilowatt at 0.8 power factor is equal to, how we are converting this 400 kilowatt into kVA, that is you have to divide by cos phi. That is, we know that kVA into cos phi is equal to kilowatt. Therefore, kVA is equal to kilowatt divided by cos phi. Therefore, it is 400 divided by 0.8, it is 500 kVA. 500 kVA means what is the rating of the transformer? 500 kVA. The load is also 500 kVA. Therefore, X is equal to 1. Means it is operating under full load condition with a power factor of 0.8. That is 500 into 0.8. What you are getting is 400 kilowatt. Next, 300 kilowatt means what? 300 kilowatt at 0.75. What is the kVA? Corresponding kVA is 300 divided by 0.75. It is 400 kVA. For 500 kVA, it is a full load. For 400 kVA, then how we are finding out that? It is 400 divided by 500, that is X is equal to 0.8. For 500 corresponds to 100% loading. For 400 kVA means it is 400 by 500, that is equal to 0.8 is the loading factor. Similarly, for 100 kilowatt at 0.8 power factor means it is 100 divided by 0.8, that is 125 kVA. Then loading is 125 divided by 500, that is corresponds to X is equal to 0.5. Means it is operating at full load, it is operating at 80% of load, it is operating at 25% of load, it is operating under no load condition. Then copper loss at full load. Copper loss at full load means at 500 kVA copper loss is 4.5 kilowatt. Therefore, for the 400 kilowatt means it is already we are calculating loading factor X is equal to 1, and for 300 kilowatt loading factor is 0.8, 100 kilowatt is 0.25. Accordingly, you have to calculate. Therefore, copper loss at full load of 500 kV, or it is nothing but 400 kilowatt. It is 1 square into 4.5, that is 4.5 kilowatt. Similarly, copper loss at zero point 0.8 full load or 80% of full load, that is 400 kVA, that is nothing but for 300 kilowatt. It is 0.8 square into 4.5, that what I am getting is 2.88 kilowatt. And similarly for 25% of loading the copper, because here it is operating at 25%. For 0.25% the copper loss what I am getting is 0.281 kilowatt. Then what is the total here? There is no copper loss. Next 4 hours, that is it is under no load condition. If the current is not flowing in the primary and secondary winding, then the copper loss under no load condition is treated as a zero. Therefore, as such there is no loss. There is no copper loss in the last 4 hours. Therefore, you have to find out the copper loss for 3 time periods, that is 6 hours, 10 hours and 4 hours. Therefore, it is already calculated kilowatt hour. This is kilowatt hour. It is kilowatts we are getting. And for 24 hours, how to calculate, I show you here. For 6 hours, what is the copper loss? 4.5, 6 into 4.5 plus. For next 10 hours, what is the copper loss? 2.8 kilowatt, 10 into 2.8. Similarly, next 4 hours, that is this 4 hours, it is 4. At this, the copper loss is 0.281, 4 into 0.281. And last 4 hours, there is no zero copper loss, therefore 4 into 0. Therefore, what I am getting here is total copper loss in 24 hours is 56.924 kilowatt hour. Similarly, I will calculate total copper loss in 24 hours, that is sum of that 56.924 kilowatt hour what I am getting. Then iron loss in 24 hours, that is iron loss is given 3.5 kilowatt for 24 hours we have to calculate, because it is irrespective of the loading condition. All the 24 hours the iron loss remains the same. Therefore 24 into 3.5 what I am getting is 24 kilowatt hour. Then the total transformer loss, that is what I am getting here, is 56.924 plus 84. These two are the total copper loss in kilowatt hour what I am getting. Then transformer output in 24 hours, how to calculate? That is already given here. 6 into 400, 10 into 300, 4 into 100, 4 into 0. Therefore, I am calculating here transformer output 6 hours 400 kilowatt, 10 hours 300 kilowatt, 4 hour 100 kilowatt. Last 4, it is 4 into 0, that is 0. Therefore, total kilowatt hour output is 5800. Then efficiency, we can output by output plus losses. It is 5800 kilowatt hour is the output. Output kilowatt hour is 5800. And total iron and copper loss for 24 hours is 140.92, 140.92. What I am getting is 0.976, or it is 97.6%. Then the another numerical I have got here, find the all day efficiency for 50 kV distribution transformer having full load efficiency of 94% and full load copper loss of constant iron loss. The total transformer is as follows. It is a different loading factor is given. Just I am calculated here. Just you have to go through this problem and you have to try to solve it. And if you have got any doubts, then you can discuss with me in the subsequent sessions and live classes. Okay. This is how you have to calculate the efficiency, all day efficiency of the transformer.